We are recording. So welcome everyone. I will try to share my screen. Okay, so we have here our talk today is about anti-fragile software design. So I repeated the introduction that was also in the first meeting, and then we'll see the example of how we can build a software design that is anti-fragile. So first of all, this idea of anti-fragile was created by this very important book author called Nassim Taleb, who is originally from Lebanon. He's a Christian, and he lives in the United States now for many years. And he wrote two other very famous books. One was the Black Swan book that you should be familiar with. It also became a movie. There is the Black Swan movie. And also he wrote a book called Fooled by Randomness. But this is my favorite book, The Antifragile, because he's creating a new idea. And this new idea, this new concept is something that normally we don't think about. Normally we think about things that are either fragile or the opposite of fragile is robust. So fragile is something that is easy to break it. And in his definition, when exposed to volatility, it is prejudicial. And like this glass, it's very easy to break it. And something robust are things that are immune to volatility, so they not break easily, like this stone. But Nassim Taleb says there are things that are anti-fragile. So they like volatility, they like changes. So volatility is beneficial to them. And this is anything that can evolve. In any system or any situation, you can have evolution, so change is good. Volatility is good because volatility is helping the evolution. And so if you look at these three kinds of things over time, so the fragile things, they will break, they will suffer a process of erosion or deterioration. The robust things will more or less stay the same, they will not change. And the anti-fragile things will evolve, they will get better, they will improve. Okay? So these are how they react over time. And so this idea of anti-fragility is much more than resilience and much more than robustness. And we are not just talking about objects or systems that are resistant to change. We are talking about things that will become better. And that in the future, they will be better than they are now because they will have this process of evolution. Okay? And this is related to decision making. In the field of decision making, everything that is close to us, that is near us in time, is more predictable. And everything that is far from us becomes less predictable, or it becomes more unpredictable. And the main concept here that instead of building things that will try to predict what is going to happen, we will build things that can evolve, that can have an evolution. So we don't need to predict. And this is a very important concept. If I can build a system and this system can suffer a process of evolution, and I can guarantee the mechanisms of this evolution, I don't need to predict what is going to happen in the future. I don't need to know what's going to happen in the future. I just create the appropriate mechanisms that enable this evolution. That is basically what happens to biological life forms like animals and plants, they have their DNA and they have evolution, and they can create mutations, and they can survive and adapt. Okay. By the way, all this concept of evolution is not against Judaism, or we should say the opposite. Judaism, the Jewish religion, is not against the concept of evolution. This is a big misconception. Okay? And people who don't understand what's written in the Bible, in the Torah, but I will not talk about this now. This is the topic of some other presentation. So, any question until now about this concept of the antifragile and the evolution? Any question or any comment? Okay. So in the part one, we saw that volatility in software design is what we already know from the Lehman laws of software evolution, that if there is a software system, we need to continuously adapt it, because if we don't adapt the software system, it will become less useful. Okay, so if you want the software system to be useful, we must always adapt it to the changes that happens over time. In our case, is the changes in requirements, and there are two kinds of changes in general in software system. There are functional changes and there are non-functional changes. And this is a very important concept. Functional changes, we want to implement new requirements. And this has an impact on the behavior of the system, on the functionality, on the features. And there are also non-functional changes that we may need to do to improve the quality. So for instance, we do refactoring. And when we do refactoring, we want normally to reduce the technical debt. So again, these are very important concepts that I will not explain in detail in this particular presentation, but you should know what is refactoring. You should know what is technical debt. Okay? Let me make a stop here in the presentation just to see you. Okay? So, do you have any question? Do you have any comment? We have here a person called Isaac. Isaac, is it Isaac from New York?
Hey, Chaim. Yes, it is Isaac from New York.
Okay, welcome. Okay, so
Yep.
now you are our first international guest today. So Isaac, we are here. You see the other people. We have here
Yep.
most people from the Do You company, but from Margin, you see here Dennis and Tal, and other people here who work with me on different projects on different companies. Okay.
Nice to meet you all.
Yeah. Okay, so let's continue the presentation. And so wait. So in the previous session, we talked about the barbell strategy. I will not repeat it now. I will share with you the recording. You can see the explanation of this strategy to make systems more anti-fragile. And I wanted to talk to you today about the second strategy, which is this, about the composition. This is a very interesting concept. You can take many parts that are fragile and assemble them together and build something that is anti-fragile. Okay, this is a very interesting concept. Like you see here, there is this big fish the big fish is trying to catch the small fish, and perhaps the big fish will be able to catch a few small fish, but all the small fish together, they will survive and they will continue to evolve. So, and this is the case of all different kinds of animals that live in communities, like ants or bees. That you may kill a few ants and you may kill a few bees, but the community of ants or bees can survive for a long time and continue to grow, and despite that its members are very fragile. Like an ant is very fragile. It's very easy to kill an ant, right? So the idea of a componentization is not new. It's a very old idea in software design. And the goal is that when we divide the software system into components, uh, when we make a change, this change should only affect a few components and not all of them. And we try to avoid the change to affect all the components in the system. Okay, and we, in order to be anti-fragile, we want the system to benefit from the changes in the environment. Right? This is the definition of anti-fragile. That is, it's not only surviving. It's not only about adapt. It's not only to be able to adapt. It's to benefit. It's to become better. You have a better system. And we can do this. One of the ways to do this is when we have several systems that have the same components. And I'll give you some concrete example of a systems that have the same components. And then when we improve the component in one of the systems, the other systems that use the same component, they can benefit from this improvement. Okay, so now this is this is the abstract concept, and let's see some concrete example. So here you see these AA batteries. These are the common regular batteries we use in all kinds of devices. And on the left side, you have the regular battery that is a throwaway. You use it until it ends, and you throw it away. But on the right side, you have the rechargeable batteries. Okay? That is also is not something new, but it's relatively new. Okay? It's not so old as the old batteries. Okay? The old batteries are probably, I don't know, more than 50 or 60 years old. When I was a child, there were regular batteries, but there were not rechargeable batteries. I don't remember having any rechargeable battery when I was a child, kind of in the 70s of the previous century. But if you pay attention, these batteries, they have exactly the same shape, and we could say that they have the same interface, right? You can, if you take a look on the battery, it has an interface on the extremes, and on the top and on the bottom, it is the interface of the battery. And because these two different kinds of batteries, they have the same interface, we can benefit from improvements. So when people invented these rechargeable batteries, they could be used in all the millions of different devices that already use the previous kind of battery. And so all the toys, all the clocks, all the electric devices, we could now use rechargeable batteries because they have exactly the same shape, the same size, the same interface, right? So this is a very concrete example of evolution of a component, and this evolution of a component uh, benefits the entire ecosystem of all the different systems that use it. Okay, so this evolution of the battery benefits all the millions and millions and millions of different devices and toys and clocks and anything that uses these batteries. And now we have some new guests. We have Nico. I guess it's Nico Codina from Argentina, right?
Correct, Hayim. Hello.
¿Cómo estás, Nico?
Muy bien. Aquí estamos.
Okay, so now we have one guest from New York, one guest from Argentina, and we have Andrea. Andrea is our Italian guest, but he's an Italian guest in the train, in the Israeli train. Okay, have a nice trip, Andrea. Okay, so let's continue the presentation. Okay, so this is an example of evolution, and of evolution of one specific component that benefits the entire ecosystem. Now, let's see software examples. In the case of software, it's very important to have principles for the decomposition of software systems. And the two main principles that you should know are coupling and cohesion. Okay? You must understand coupling and cohesion. And coupling is like how much related are two different models. It's the degree how dependent these two different models are to each other. And cohesion is how strong is the relation of the functions performed by the same module. So if I have one component in my software system, the cohesion is a measure of the strength of this connection between the different functions that are performed by this specific module, this specific software component. And the coupling is a measure of a connection between modules. If I have two modules, I can have the coupling between them. So I always want to have low coupling and high cohesion. I want the coupling to be low, and I want the cohesion to be high. Any question about that? No, this is very important principle. Now, we'll see 5 examples of decomposition in software systems. Some of them are very old, and others are much more modern. Okay, so we talk about dynamic linked libraries, object request brokers, service-oriented architecture, microservices, and software product lines. And here we have Lego. Okay, Lego was one of my favorite toys when I was a kid. And now I have a daughter. I invested lots of money buying Lego blocks to my daughter, but she didn't like it very much. But in total, I spent hundreds of dollars buying Lego blocks for my daughter. Now, let's talk about examples of components in software systems. First, the idea of the dynamic linked library. This is a very old idea. It existed in several different operating systems, which is basically a mechanism to share code, right? It's a mechanism that enables us to have a library that is called dynamically, on runtime, by some other application or some other program. And the idea is that there are many programs, that are many applications using the same library. Okay? So this is an example of a component that is shared. Okay? This is a component that is shared among many programs, many applications. And we don't need, when we make an improvement in the library, we don't need to recompile the applications because there is, well, let me stop sharing. Someone is making some noise. I'll mute people who are making noise. Okay, so let's continue. So when I make a change on the library, I don't need to change the applications that are using the library. Okay. Let's see. So this is a very old example. See, a more modern example from the 90s is the object request broker. And the object request broker was a very elegant because it enabled connections among objects that were distributed on the network. So the orb from one side enabled a distributed system, and from the other side, it also enabled connections among objects that were written in many different programming languages. So for instance, in the year of 1996, that is 28 years ago, I worked for IBM in Haifa, in Matam, and I developed an application using Smalltalk. Smalltalk is a pure object-oriented language. It's a 100% object-oriented language. And this COBOL application, this Smalltalk application called an object written in COBOL. COBOL, Common Business Oriented Language. I'm talking about 1996, 28 years ago. Okay, so I had this Smalltalk application called an object that was written in COBOL. This is a very non-object oriented language, right? And this was done using an orb that provides this decoupling. So the idea of the orb is that you have an interface repository. Each object has an interface, and the client application calls through the object request broker, and the object request broker makes the mapping between the request from the client application and the object that is receiving the call, which is the servant object. Okay, so from the side of the client application, I have an interface stub, which is in a language called IDL. IDL is an interface definition language. It is an abstraction. And in the side of the servant object that implements the functionality, I have the IDL skeleton. So this interface definition language is an abstraction on both the client side and the server side. Okay, and the orb is the broker in the middle between them. So this is very elegant because this enables you to build a distributed system in which you have many objects that you don't need to know the location of the objects. You don't need to have an address. You just call the broker, and the broker will send the request to the right object. And these objects, as I said, can be implemented in different languages, different programming languages. Like I gave you an example, one object written in Smalltalk, another object written in COBOL. And then I can take my servant object and I can improve its implementation, and all the clients that use the same servant object will benefit from this improvement. Okay? So this is similar to the concept of the library, but is in a distributed system. It's not on a single machine. It's not on a single computer. It's a distributed system. Okay? And this is in the 90s. Okay? This is 30 years ago. Now, from this idea of the object request broker, we have evolved to the concept of service-oriented architecture. Okay? Service-oriented architecture is much more modern. And here you have on the left side what was before the service-oriented architecture, when we had this kind of monolith, like the software system. It was one big software system doing everything. And then on the right side, you see the service-oriented architecture, that you have many reusable business services. Okay? You see all these different blocks are reusable services, and they can be used by different applications. So, for instance, you see here these circles show who is using each service. So the create invoice is being used by the account management, and the check customer status is being used by the order processing and by the scheduling. And the check order status is being used by the processing and by the account management. And the check credited is used by the order processing, and the check inventory is being used by the scheduling and the order processing. So these different systems, these different business services are being used by many different applications. Okay, so there's lots of software reuse, and they are isolated in components. There are some very clear interfaces between them, so there is a very low coupling. And this is very different from what you have on the left side, that is the monolith. In the monolith, everything is together in a single software system. Okay? And regarding the software-oriented architecture, we have here the 9 principles of software-oriented architecture, this is something that you should learn. Okay, so this is a homework I'm giving to you now, if you need to learn about the 9 principles of software-oriented architecture. And I will just say the names of the principles, and then later you need to read the explanations. Principle number 1 is to have standard contracts. Each service has a standard contract. Principle number 2, loose coupling. We talked about that before, that the coupling should be low coupling. Principle 3, abstraction. The interface must be abstract. Principle number 4, reusability. We want the services to be reusable. Principle number 5, autonomy. They should not have many dependencies on each other. Principle number 6, as much as possible to make them stateless and not stateful. Each service ideally should be stateless. And this is very important, for example, for scalability. It's very easy to scale a system if its subsystems are stateless. Principle number 7, discoverability, that you can discover the service. That you need some API, you need some interface, you can discover which is the service providing this interface. Principle number 8 is about composability, that you can combine together these different services to create new applications. And the principle number 9, interoperability, they can operate together. Okay, so I will not make a full explanation of these principles, but please study. And this is very important. All these principles of service-oriented architecture, they apply also to microservice. Okay, so every microservice architecture is also a service-oriented architecture. Okay, so if you want to do a good microservice architecture, you need to use the service-oriented principles. Here I have some explanations, but about the reusability. The reusability is the most important aspect for the evolution of the applications. Okay? And here there is some explanation. They can express agnostic logic. Agnostic logic means that they do not depend on which application is using them. And the goal here is to create these components. Okay? So this principle of reusability enables evolution. And this enables systems to be anti-fragile. And now we have the idea of microservices. Microservice is itself an evolution of the service-oriented architecture. But of course, the idea of the microservice is taking this on scale in which each microservice can be deployed on multiple instances on the cloud, which makes it, of course, a distributed system. For each microservice, you have a load balancing. So the load balancing is distributing the requests among the instances. So for each kind of microservice, I can have many instances, and each instance is handling part of the request. And I can have many different messaging channels among the different applications and my microservices. I mean, one possibility is to have a REST API, which is a HTTP request, but there are other possibilities. For instance, a microservice can be handling requests that it's receiving through a message queue. So for instance, we have mechanisms like a RabbitMQ. What's RabbitMQ? It's a message queue that I can use to deliver requests from my application to some microservice, decoupling them. Or I can use in the AWS environment, the Amazon cloud environment, I have SQS, simple queuing service. The simple queuing service is a queue that sends requests through microservices. So the microservice is listening to the queue, and when it receives a request, it consumes the request, executes it, and produces some response. Okay, so these requests coming from the applications, you can see they can come from the cloud or from a mobile device or from a web application. They do not need to be a REST API. It is very common to use REST API, but there are other possibilities. Okay? So we have all these microservices operating in this cloud environment. They can use publish subscribe interface and handle events, and they can use here from the environment all kinds of operational capabilities. And so all these things you see here in the bottom, they are core capabilities that are provided by their cloud environment. So this depends on which environment you are using. If it is Amazon AWS or Google GCP, Google Cloud Platform, or it is Microsoft, you have Microsoft Azure or IBM Watson. All these cloud environments give you lots of operational capabilities, including also database, right? The database are here, are core capabilities. and you can have many different kinds of database, right? So all this microservice architecture is an evolution of the service-oriented architecture. And here I have a list of practices of microservices. Okay, so this is in addition to the service-oriented architecture principles. So one of them is separated build. The separated build says that each microservice, I can build it independently from from the others, and each microservice has its own version. Okay, so I can deploy one version of one microservice. Again, this is independent deployment. I can take all the system that is running and deploy one microservice with a new version. Separated data stores. Ideally, all the database, all the data stores should be separated by microservice. Because as you can imagine, if you have several microservices using the same database, you can create corruption. It's very easy to have situations of corruption in the database if it is being accessed by many different microservices. Independence of platform. This means that the right way to deploy a microservice is in containers. So for instance, Docker. You create Docker containers to deploy the microservice, so you don't care about the platform. It is running on Docker. Individual technology choice. Each microservice can be implemented using a different technology. For instance, a different programming language. So you can have one microservice written in Python and a different microservice written in Node.js. Confinement of failure. If there is a failure, this failure should be confined into a particular microservice, and we should avoid it to propagate to other ones. Okay, so there should not be a crisis in the system because there was a failure in one microservice. And finally, independent scalability. So each microservice can scale independently from the others. Yeah, so you can have several instances of the same microservice. And in order to do that, it's important that each microservice is stateless and not stateful. And as you saw here in the diagram, each microservice has its own load balancer. See, here I have one load balancer, another, and another. So here, when it's written here, microservice A, there are several instances on the cloud. Okay, several instances, each one running in a distributed environment. Okay, so these are the practices of microservices that complement the principles of service-oriented architecture. So at any point, I can deploy a new version of one of the services without affecting the others, because I'm preserving all the interfaces. So each time one of the services is improved, and I have several applications using the same services, all these applications are benefiting from this improvement. So the collection of systems, this collection of applications that are using the microservices, they are anti-fragile because there is a process of evolution. Now, each new version is an evolution, and they are all benefiting from it at no extra cost. So you see, this is very powerful. Finally, let's talk about software product line. So this concept of a software product line is a very interesting concept in which you create a kind of a factory that you don't want to create a single system. You want to prepare to create many different applications. And in the software product line, you can have coexisting versions of each component. So you can have one application that is using one version of one component, and you have another application that is using a different version of the same component. And each time I have a new version, all these products of the software product line benefit, and they can be upgraded. Again, so if I am a software company, I can use this approach of the software product line and create many products using the same components. So let's see here, this table is the summary of what we discussed until now. On the left side, we see what is the anti-fragile, and on the right side, what is fragile. So if you have many programs that are linking to the same dynamic link library, this is anti-fragile. But a specific version of the DLL is fragile because you have to change it. If you have many clients using the same object with the object request broker architecture, this is anti-fragile. But the implementation details of a specific object is fragile because you have to change it. Eventually, you have to change it. In the case of a service-oriented architecture, if you have many systems using the same services, this is anti-fragile because there is evolution. But implementation details a specific service is fragile because it will have to change. And the same with the microservices. Many applications using shared microservice, they together are anti-fragile. But the implementation of a specific microservice is fragile. And if you have a software product line, several products using the same components are anti-fragile, and the specific component is fragile. Alex, you want to say something?
Yeah, let me be a devil's advocate for a second. Like, we are old guys. We're always thinking about other things. In theory, all these things are very good. But there are several basic principles that we are forgetting and not stating. Like, for example, the interfaces are not changing. Because the moment the interface changes and you have a different application or different services, well, whether that's a library, a service, it doesn't really matter, a component, in the same system, you start having a hell, not the DLL hell of the famous other ones, but the hell of the testability. What you need to test and how you need to test and verify that all the things works together. And by the way, if you look today, what's happening in the world, that basically nobody's testing anything, specifically in the cloud. They let the customer base to test it. And we see that, not from usability perspective, but from working perspective all the time. So this is all this good. There's great principles, but we need to manage those complexities as well. Not only the complexity of making those things anti-fragile and independent and component and all the nice abilities, but also to keep the number of variations, the variability points intact.
Great. So this is a great comment. And also here, there was an evolution. Let's see what was the evolution. In the case of a dynamic link library, there was a function call. And when there is a function call, if you change the interface, it breaks everything. Okay, so in the case of DLL, there was a very common problem with new versions if the interface changed, because it was a function call. In the case of the object request broker, it was already a bit better, because there was this concept of the interface description language, which was an abstract language, and then it was a bit easier to make these interfaces more backward compatible, but it was not good enough. Okay, so also in the case of the interface of the object request broker in the interface description language, you could break everything by changing the interface. In the case of service-oriented architecture, we started working with REST APIs. And REST APIs, they are very useful because you can have optional parameters. And so some of the parameters are mandatory and some of the parameters are optional, as in the case of a JSON object. So if you make a post request on a REST API, and this post request in the body of the REST API, you have a JSON object. This JSON object may have some mandatory fields and some fields that are optional. So this makes much easier to create an interface that is backwards compatible. If you only add fields that are optional. And also in the case of the microservices, if you are using some publish subscribe model and message queue, such as the RabbitMQ or SQS, normally the request that is being sent into the queue is in the form of a JSON object. So also this request may have mandatory fields and optional fields. Okay, so of course, this does not solve the problem of backward compatibility. In any situation, if you add a new field that is mandatory, you break everything. But in modern software systems, as long as you add optional fields, things are supposed to continue working. In my personal experience is that if you do a good work of domain modeling, you are able to capture everything that is mandatory and enable the evolution with mostly optional fields. But of course,
if I may, Hayim, you are talking about the technique, which is a third level. I mean, how you do those. My comment was more about the complexity of multiple objects or multiple components running together, especially if you need, for some reason, to have several versions of the same component running in the system, supporting some other applications. Because you never have, you cannot do everything in parallel, okay? In a sense, you just always do those things. So of course there are rules, and I've been working lately in the last couple of years with protocol buffers a lot. And even in protocol buffers, you have this ability of creating message-based information which is backward compatible, but you need to put work there. It's like, it's like death. It's like entropy. If you don't do that, your entropy explodes. You need to do and follow the rules. And if you break the rule, everything will be breaking. So that's, it's kind of, I'm not negating the idea I'm just adding to the last complexities on the deployment side, not only on the design and development side.
Yeah, great. Yeah, no, I think this is a very important observation. In the end, the most important aspect of our work as a software architects is to define a good interface.
Interfaces,
Right?
yeah. Software
A good
architecture is
interface.
about interfaces, design is about data structures.
Yes, and if you think about low-level design, it's also the same. Now, in the case of a low-level design, you have the methodology. Let me stop. No, you have the methodology of test-driven development. What is test-driven development? It's just about interface. Now, if you
No,
use TDD,
well, the TDD is more about requirements, less about interfaces, but you can always go through those things.
no, but if you use TDD, if you use a test-driven development, the first thing you must do is the interface, and then from the interface you create the unit test, and from the interface you implement the classes. But the first in TDD, the first thing you do is the interface, right?
You can say that. I'm looking on TDD from the different perspective. TDD ensures that you do proper regression testing. That's what it ensures. So if you introduce some changes which break something, you will find it out because you already have the test suite, and you can redo the code. And interfaces, of course, yeah. But I don't want to quarrel. It's just another level of complexity to the topic of building robust systems.
Yeah, but you know, Alex, that some people say that instead of test-driven development, it should be called test-driven design. Did you hear that?
Look, I'm not a the big lover of TDD. I think TDD is good only for some, and let's say something like 60% of applications. But that's a different story. Okay, you can call it whatever it is. The whole idea that you create first what I like there, it's the regression testing. So you have to do regression all the time, and it goes together with the proper DevOps principles and CI/CD. Actually, not an integration, the D is more important. And once again, all the testing cycles in all the systems. It's a long journey, as a matter. The same.
Yeah. Let's have another session to talk about this also. So
Okay.
my the conclusions today is that one very simple strategy to make systems that are anti-fragile is to build them using components and the shared components. And every time we improve one of the components, this component, all the systems will benefit from this improvement. Okay, so that's it. And I will stop sharing. We have a few minutes left. Any comment, question, criticism, joke, anecdote?
The joke goes about the DLL. DLL is beginning of 90s when finally Windows NT came in, which is basically based on VMS, and shared libraries are from the 78. So so for all these people who think that the DLL is the beginning of the information, no, it's not. There've been some things before that and some principles even there. And the whole idea of shared libraries is coming from the virtual memory systems. So basically, until there were no virtual memory systems, you have different management of memory, and then that came the idea. And actually, using the shared libraries evolved into some more. And once again, like every technology, if you abuse it, you can go into infinite loops. The famous DLLs and the versions and so forth. And by the way, the semantic versioning is very important in versioning your components, which ensure, especially in the discovery system and stuff, which ensures that you do have compatibility between the variants. Whenever you introduce something new, you don't break the previous interfaces. And this came from all these changes in the last 50 years or so. Smile, guys, smile. You are all, everybody very serious.
Thank you for sharing that. And Chaim, it was great to get your insight on all of this. And it's often that we have bits and pieces of information that we work with, but it's good to be able to have a cohesive kind of view on everything, because it's very easy to forget the value the cost benefits of every single type of architecture and how we got there and the context for it. And I would say one suggestion for the slides, I don't know if you covered it, and I wasn't here from the beginning of the meeting, but I would say multi tenant architecture is probably part of your microservices and service oriented architecture as well. Probably good to mention that.
Yeah, thanks. Yeah, it's an interesting aspect that really I didn't mention. Yeah, it's a good idea. Thank you, Isaac. So look, our time is finished, and I need to go to another meeting. So thank you, all of you, for being here today. I hope you enjoyed it. I hope you learned something, and I hope I'll meet you again soon. As we say in Hebrew, רק בשמחות. רק בשמחות, only happy moments. Okay. תודה רבה.
Thanks, Chaim.
Thank you, Chaim.
Thank you, שבוע טוב לכולם.
Thank you.
Bye.